Welcome to Ethers and Epoxides. Ethers and Epoxides. Another functional group in this chapter is called Thiols, ethers, and we'll briefly just mention Thiols ethers, but the main focus is going to be ethers and epoxides. So I'd like to introduce the physical property and the structures of ethers and epoxides. You do have some problems associated with those. And then we're going to go straight into your POGL activity. PG17. Well, actually, before we do that, I will do synthesis of ethers and epoxides. And so you will see that we have one way from alkenes to make epoxides, and to make ethers we have two ways. So those are reactions to make ethers and epoxides, and then we'll do POGL 17, which is the reactions of ethers and epoxides. And that'll conclude this chapter. Okay, so first, what is the functional group of an ether? So this is water. This is an alcohol. We've got water. We've got an alcohol. And if we replace one of those hydrogens with another carbon or an R group, we have an ether. Some common ethers that you use a lot in the lab is THF, which is tetrahydrofuran, and this is a solvent. Another one is diethyl ether. So you can see that both sides of here are two carbons, so that's diethyl ether. They can be symmetrical or not symmetrical. So if you have something like this, you would do the ethyl methyl ether. So you name one part and then the other part, and it's alphabetical order. Okay, so what about the structure? Water, what's the hybridization of water? That oxygen is sp3, and it's going to be bent, right? Alcohol is sp3 because it's that oxygen is connected to four things. Here, sp3. So you have an sp3 carbon, and it's going to be bent like water. So this is actually going to have both these lone pairs on the same side, and it's going to be not 109 degrees, but it's going to be less than 109.5 degree angles. Okay, what about the polarity of the carbon-oxygen bonds? The carbon-oxygen bonds, of course, are points towards the more electronegative lone pair. So overall, just like water, your dipole, your molecular dipole is that way. Here, your molecular dipole would be towards those lone pairs. This would mean that you have dipole, intermolecular forces. So the intermolecular forces that govern your solubility properties and your melting point and boiling point properties would be dipole. And in fact, this is pretty weak. So like if you have an aldehyde or a ketone, that's going to have a carbonyl, which has a stronger dipole interaction. Okay, so this ethers are considered weak dipole, and so that means a compound with the same molecular weight would have a lower boiling point or melting point. Now, so like a lot of your solvents, so you can look at like in butanol, which is an alcohol, and has a molecular weight of 74, its boiling point is 118 degrees Celsius. So you look at something like tetrahydrofuran, THF, and it has a molecular weight of 72, which is very close to 74, and it has a boiling point of 66 degrees Celsius. So this is a significant difference, and this is because it does have a weak dipole-dipole. The butanol has hydrogen bonding, and we've talked about how hydrogen bonding has a higher intermolecular energy dissociation with it. Now, because it has lone pairs, so let's look at tetrahydrofuran. With its lone pairs, it can accept a hydrogen. So it can, which helps with solubility. Ethers are widely used as solvents, and let's just look at why we would use an ether solvent. Remember, the solvent is what you dissolve your reactants and your reagents in the reaction. They need to be inert. It means they need not to influence the nucleophile and the electrophile in a way that is not productive towards your reaction. So the nice thing about ether solvents, they can dissolve both nonpolar and polar substances. And this is important because a lot of your organic starting materials have a lot of carbon, which makes it nonpolar. And then there's also functional groups that make it polar. A lot of your reagents are polar. And this is a very important point here. They're unreactive towards strong bases. Okay, so then that's a hard thing to find, right, in a solvent. Let's look at a strong base. So a Grignard reagent. So a Grignard reagent looks like something like this. And this would be considered a strong base. And if you want to know how strong, well, this is pretty much a positive. This means the carbon's a negative. And like, let's just put it in water. Okay, so let's do that acid-base chemistry reaction. So this carbon here will take the hydrogen off of water. And now you have, that's a conjugate acid over here on the product side, and you have magnesium bromide, and it's going to make a complex. This will be a salt. You'll see a white precipitate, the conjugate base. Now what we care about is assigning pKa values to see which way this equilibrium goes. 15.7 for water, and for methane we have a pKa of 50. Okay, so that's like 36 zeros. Okay, I'm not going to draw all these out, but you get the point all the way towards the product. And so that's a pretty strong base. And you can put Grignards have to be pretty much in ether, so you'll put that in tetrahydrofuran. Okay, crown ethers, they are really kind of cool. They solubilize metals. So this is what a crown ether looks like. And they will form a complex with like a metal like lithium. So a lot of times if you have a metal that's you want to make your nucleophile naked, so like a lithium CH3, if you put a crown ether, it will trap this metal, and then you would get, it's called a naked anion. And this is really nice because now you have a very, very strong nucleophile because you have freed up those lone pairs. So that can really make a difference in your reaction. The way crown ethers are named, this would be a 12 crown 4, and it's because you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you have 12 atoms, and you have 4 oxygens, 1, 2, 3, 4. And so it's called 12 crown 4 if you were to order this. And it will solvate lithium because lithium has a certain size. If you want to solvate like potassium, potassium is bigger, larger, and you would need something like an 18 crown 6. And you can see 18C6 to solvate potassium. I will tell you that if you ever use these crown ethers, you have to be very careful. They're very toxic because if you these crown ethers are non-polar, they will go through your skin and dissolve and get into your blood, and they can precipitate out potassium from your blood, which can cause an immediate heart attack, or it can even cause a heart attack like 2 days later. So it's very dangerous. So double glove or don't use them. All right, so you can look at your slides on the different properties of ethers. Let's just talk about how to synthesize these ethers. So ethers are made by, we've talked about if you take an alkene with mercury acetate and you put this like in methanol. So if you put this in alcohol, this is reviewed from Organic 2, and then you treat this with sodium borohydride next, you will get your mercury acetate mercurium ion, and then your methanol here will be your nucleophile, and it will attack from the more substituted carbon, and you get OCH3. Then here's your mercury acetate. When you add the sodium borohydride, that will basically replace, the hydride will replace the mercury acetate. And so you will have this ether. And this follows the Markovnikov rule. Okay, so that would give you Markovnikov substitution. Okay, that's one way to make an ether. And I would make sure I get these on my reaction sheet. So that's one way to make an ether. The other way to make an ether is the Williamson ether synthesis. So Williamson ether synthesis, you need a alkoxide plus a primary alkyl halide. So those are the two things you need. And so an alkoxide would look like this, which is a strong base. You saw this when we were doing elimination reactions. And then a primary alkyl halide would look like something like this. And so this is an SN2 reaction. And this does backside attack. The bromine is your leaving group. And then you can see that you have made, in this case, dipropyl ether. Okay, now you do have to have a primary alkyl halide, and the reason why is because you would have competition with in E2. So it would not be a clean reaction. So if you use something like a secondary alkyl halide, you would get such a alkoxide base would also take the beta hydrogen here, and it would choose this hydrogen as opposed to the other beta hydrogen. So you could follow Satsev's rule, and so that would take that, and you would get the alkene. Okay, and that's not what you want. You're not trying to make an alkene when you're setting up your reaction. So if you want to do the Williamson ether synthesis, you'll use a primary alkyl halide. You could also use an allylic alkyl halide, or benzylic would work fine, or even a methyl. Okay, but you don't want to deal with secondary or tertiary. Okay, that's how you make ethers. To make an epoxide, we saw that you could take an alkene and you could react it with MCP MCPBA, which is metachloroperbenzoic acid. And this will deliver this oxygen here to, you have a transalkene. So this is syn stereochemistry. And here you have, you just make sure you maintain that. Okay. And this is your epoxide. This is the oxygen that got delivered. And then you get, this becomes the acid. Okay. So that's MCPBA. You usually use that in dichloromethane because you want a nonpolar inert solvent. And dichloromethane looks like this, which is nonpolar because it has symmetry and cancels out for the most part. Okay, so that's how you make epoxides, and that's how you make ethers. Now, I'm going to do the POGL activities to talk about the different reactions that these epoxides and ethers undergo. Two things I want to say about the thiols and thiolates, and you're welcome to read those. So your thiols are, it's just an alcohol-like with sulfur. And sulfur is right underneath the oxygen in the periodic table. So sulfur, it has an expanded octet because it's in row 3. So it can do things that the alcohols can't do. This, but it's also behaves a lot like alcohol. You can think of it as using forming 2 covalent bonds plus 2 lone pairs for its what I call a happy atoms, meaning no formal charge. So we also talked about thiolates. You've seen these. This is a thiolate. This is a strong nucleophile. Thiols are going to be stronger nucleophiles than oxygen because they're larger. They're more polarizable. I mean, they have this big electron cloud. And one other thing with the alcohols, how do you make an alkoxide? Well, usually you use sodium, or you can use sodium hydride. If we use sodium hydride, this is just an acid-base chemistry, okay? So this hydrogen is a negative here, and the negative will take that hydrogen, and then you get hydrogen gas, which is your conjugate acid, which has a pKa of about 36. And then you also get your conjugate base here. And that's how you make an alkoxide. And so what's the pKa of an alcohol? Between 16 and 18. So the difference between 16 and 26 is about 20 zeros to the product side. And you would do the same thing if you needed to make a thiolate. And those are great nucleophiles. All right, so one other thing I'm going to point out here, and regarding a Grignard. Well, let's just go on to, well, let's do the Grignard. Okay. So when you have something like a ketone and an alcohol, and you want to react this with methyl Grignard. And the methyl Grignard, you want to make this molecule here. Okay, so you want to make this molecule. Now the problem is Grignards are strong bases, and so they're going to take that alcohol OH away, and you're going to shut down your Grignard, okay? And you're going to make CH4. And then the magnesium is going to hang out here with the oxygen. And when that happens, notice you didn't get nucleophilic addition to this carbonyl that you wanted. So, and you do this in ether, so if you had this in THF, or you could just write ether solvent because you're a Grignard and that solubilizes it. What you have to do is you have to do a protecting group. And so the protecting group here is in your book, is acyl ether. And we'll also talk about other protecting groups later on in this chapter. But so if you have something like TIPS chloride, so that's triisopropyl, too many carbons, always count your carbons, triisopropyl chloride. And what you can do is then you can just add this with triethylamine, which is just a proton sponge. Okay, and that will soak up the HCl. And if you do this, then now you can protect. It's called protecting group chemistry. So if you take your starting material and you react it with TIPS chloride and triethylamine, then this is going to do, you can think of this as an SN2 reaction. A lot of times we don't think of it like that. From the standpoint, it's an expanded octet once you start getting with silica, but it basically does that. It adds, and then you have a leading group, and here's your silyl group. Silica is underneath carbon in the periodic table, and then you see how you're generating, so you end up having this, and then what happens is the triethylamine here will come and deprotonate, and you will get, as a carbonyl, and you get this silyl ether. This is a silyl ether. And then triethylamine is your, it's called a proton sponge. And so if you're ever generating HCl in a reaction as a byproduct, then you need a proton sponge to absorb it. So that way your reaction goes forward. Now, so from this you can see that you have this silyl ether. And now if you take this silyl ether, this is the beauty, this is called protecting group chemistry. And you can Google protecting group chemistry. There is a book of about 1,000 pages, actually not that many, maybe like 750 some pages, that have all the different protecting group chemistry. So if you want to look in protecting group chemistry, it's organized by functional groups that you need to protect. It's definitely, if you're a synthetic chemist, it's a must-have book. Now you can react this with the Grignard and ether, and now you can see that this will go after the carbonyl here, and you can make your compound. And then you can add some a little bit of acid, and you will quench that alcohol right here. Now you can also look, there's a thing called tea bath. tea bath as the removal, and it removes the silica. So tea bath is tetrabutyl ammonium fluoride. So tetrabutyl is 4, 1, 2, 3, 4. Tetrabutyl, there's 4 of these. Okay, ammonium, so that's nitrogen with a plus charge, fluoride. And the fluoride loves silica, okay? And their bond is so strong that this fluoride will react with silica and will deprotect that oxygen ether, that solid ether, and then it's really a nice reaction. You can just set it up at room temperature and it'll go overnight. And that's how you could get your tertiary and secondary alcohol product. So those are solid ethers as protecting groups. They are in your slides. Now let's go over Pogel activity 17. Okay, so model 1 is called ether cleavage with HBr. Now, this is not a reaction you want to happen. I've worked in the lab a lot, and this is not a reaction that, well, I guess you do want to have it in some protecting group chemistry, but usually these are unwanted side reactions that you just want to be familiar with. Because a lot of times you don't want to cleave your ether. There are some nice reagents for protecting group chemistry, though, to cleave ethers and that are specific. So I guess that is a time when you would want to cleave your ether. Okay, so here's our model, and so let's look at this. They do have to be harsh conditions. HBr is pretty harsh. Model 1, the ether is reacted with HBr. HBr is a what? It's a very strong acid. We're talking pKa. I'm going to go with less than 10, I'm going to say less than 0. That's what I do with my inorganic acids, but probably negative 10. Okay, B. 1B. In the presence of HBr, the ether acts as a, okay, see, there's your curved arrows, which is 1C. Draw your curved arrows to show the electron movement from the nucleophile to the electrophile. It's taking this hydrogen, so it's acting as a base. So this is acid-base chemistry, folks. Draw the product when the alcohol is reacted with the acid. So here on 1D, we have this alcohol, and we react it with the acid. Those electrons go there, and then you get a protonated oxygen. Compare this to the reaction of an ether with acid, step 1. Are there any difference? Okay, so here you see, I would just say it's very similar. Step 1 is called protonation. What is the purpose of protonation for either an alcohol or an ether? Well, we've learned that if you protonate an alcohol, it makes the OH2 water, which is a great leaving group. So an OH negative is a bad leaving group, but also an OHC3 or OR, R being any kind of carbon, is a bad leaving group. But if you have HOCH3, methanol, well, that's very stable, and that's a great leaving group. So we are protonating at step 1 to make the good leaving group, the OH, the OR into a good leaving group. So for step 2, of the reaction in Model 1, the protonated ether reacts with the Br minus, the anion. Label the rows as nucleophile, electrophile, acid, or base. Okay, so now we have this bromide, and it's going to attack this carbon here. And when it attacks a carbon, it makes it a nucleophile. Okay, so that makes it a nucleophile. If here the oxygen lone pairs is going after a hydrogen, so that makes it a base. Here it's going after a carbon. Now this is going to leave. So there I'm showing you that that's your leaving group. So this is your electrophile, the protonated ether. Draw curved arrows to show the electron movement. And we just did that. Circle the leaving group from the reagents. Okay, so you want to circle this leaving group. There's your leaving group. Assuming that the R prime group is primary, by what mechanism does the reaction occur? SN2. In fact, this one's showing differently. This one's showing you what I drew. So if you want to correct this, would be R, BR, and then R prime OH. But you can just go after the other carbon because it's kind of generic. Okay, so SN2 primary halides undergo SN2 the fastest. Let's see what reaction, step 3. Okay. So question number 3. In step 3 of the reaction shown in Model 1, the alcohol reacts with an additional equivalent of HBr to form alkyl bromide. Draw the complete mechanism for step 3. So here we have so what's the mechanism here? So the first step is protonation. And you will need to know these mechanisms. So step 1, protonation. Okay, so you see my 2 electron flow arrows. Okay, now we have a protonated alcohol here. And we have bromide. Now the bromide, this is a great leaving group. Okay, this is water. So this is our electrophile. This is our nucleophile. And the nucleophile is going to go after this carbon, and those water is going to leave. So there's your leaving group, and this is your new product. Okay, number 4, the reaction of thin ethyl ether with HBr, and they said excess. Okay, and they give you the product. What are the functional groups of the 2 products that are formed? So this is an alcohol, and this is a primary alkyl halide. Compare these products to the final products obtained in Model 1. Are there any differences? Well, instead of water in Model 1, in the reaction, phenol is the product. Okay, so you get phenol. Draw the mechanism above using curved arrows to show the electron flow movement. Okay, so always the first thing that happens with the oxygen is protonation. Okay, so now we get the bromide, and we get a protonated ether. Okay, make sure you get your formal charge. Now we're looking at here, the bromide chooses to go after the sp3 carbon because this is an SN2. It cannot go after this is an sp2 carbon on the aromatic, so it has to do SN2 on sp3 carbon, and that's how we get this primary alkyl halide, and this is how we get this is our leading group here, the phenol. Once your group has reached agreement to the above questions, determine whether the phenol would react further with HBr to form this. The answer is no, and it's because this is an sp2 carbon. sp2 carbons cannot undergo sp or SN2 reactions. Okay, they don't undergo S substitution. All right, now let's go on to Model 2. Model 2. Model 2, we're doing ring opening reactions of epoxides. So go ahead and draw, or start working your problems, and see if you can observe the differences between the two. Okay, so 5A. Label the epoxide in Model 2. What product forms on reaction of the epoxide under acidic conditions? So here's our acidic conditions. Do you see that that's a diol? Which product forms under the reaction of basic conditions? It's a diol. Are there any differences between the products of acidic versus basic? No. Compare the molecular formula of the epoxide. So that's C2H4O. And what about the products? The products are C2H6O2. What is the role of the water under the acidic conditions? See how the water added? Did you circle nucleophile? What is the role of the hydroxide under basic conditions? Did you circle nucleophile? Epoxides are cyclic ethers. In your group, determine why an epoxide is more reactive than an ether. Well, this is an sp3 carbon, and we know sp3 carbons have 109.5 degree bond angles. Well, in a triangle such as this epoxide, you have 60 degree bond angles. So this is very strained. And so epoxides, you know what they do? Epoxides open, and that relieves that 60 degree strain. Consider the basic catalyzed opening of the epoxide Model 2. What reagent has been added to the epoxide? This is the OH. Label the roles of each reagent involved. So this is a nucleophile, and then your epoxide is your electrophile. Draw curved arrows to show electron movement in this step. So here, those electrons will go here. So you see you have two electron flow movements. Question number 7. Consider the acidic catalyzed ring opening. Draw curved arrows. Okay, so we have acid, and the first step is called pronation. And you'll have to be able to do this mechanism. So the first step is you have pronation of the epoxide. That's step 1. And so there's your two curved arrows for step 1. Okay, so now for 7B. Draw the mechanism for the protonation of an alcohol. So if we did an alcohol here, an acid, which we've done before, the alcohol gets protonated, and you get water. Compare the difference, or compare the protonation of the epoxide. What is the same and what is different? Well, the oxygen's getting protonated. The protonated oxygen has a formal charge of +1. The only difference is the alcohol has a hydrogen, whereas the epoxide has a carbon. What is the purpose of protonation of the epoxide? Well, we're going to open that epoxide. Okay, so it's kind of making a leaving group, a better leaving group. So now in the second step, okay, so the second step here, which we'll draw right here, the mechanism, identify the nucleophile and the electrophile. So the water now is going to be the nucleophile, and the protonated epoxide is your electrophile. And there's your curved arrows. What process must occur to convert the product of step 2 to the final diol? Well, the epoxide has to open. So when the nucleophile attacks, you get this here. And if you make this the blue, you can see, yes, it's protonated, but then you have another water that will come in and do a third step, which is called deprotonation. And that regenerates your acid catalyst. Okay, once your group has reached agreement on the above questions, draw the product that would form if the acid catalyzed opening of the epoxide was conducted in acid and methanol. So what if we did this reaction in alcohol? So there's our epoxide. And what if we did it in some acid catalyzed methanol? Well, step 1, you get protonation of your epoxide, which would activate it towards this nucleophile, the weak nucleophile. And now you would get and of course this is still protonated, and then you'd have to have your water regenerate your acid by doing a third step of deprotonation. And so you would have a ether, that's an ether functional group, and an alcohol. Let's do model 3. So model 3 is very important. You're going to be talking about the regiochemistry of reactions with unsymmetrical. So if you have an unsymmetrical epoxide, then you need to really pay attention to the regiochemistry. And these are going to be different under basic conditions versus acidic conditions. And you can see here that your nucleophile adds to a different carbon. Let's clean this structure up here. Okay, so what nucleophiles do you have under acidic condition? Water, just some kind of alcohol. Under basic conditions, notice you have hydroxide, which is a charge. You have alkoxide, which is a charge. and then you can have a Grignard, which essentially is a negative carbon. Okay, 8. Under acidic conditions, the nucleophile attacks which? The more or less substituted. So it's attacking this carbon. So under acidic conditions, it's attacking the more substituted. Under basic conditions, it's attacking the less substituted. Oh, and it asks, so what nucleophiles under acidic conditions? Are they strong or weak? Well, they don't have a negative charge, so these are weak nucleophiles. Under basic conditions, these have a negative charge. They're basic. If the nucleophile is the same for the acidic and basic conditions, the relationship between the two products would be, so they have the same molecular formula, but they have different connectivity. What would that be? Constitutional isomers. Consider the acid catalyzed opening of the unsymmetrical epoxide. So this is your unsymmetrical epoxide. The pronate epoxide would be more or less reactive. Well, when it's protonated, it's more reactive. So once that epoxide is protonated, that's going to be more reactive because it's a better leaving group. Based on your answer, what kind of nucleophiles under acidic conditions? So you see how you have weak nucleophiles under acidic conditions? And that's because you have a more activated epoxide. Now also, you can't have acidic conditions and basic conditions, because what if you added H3O plus and sodium hydroxide? Then you're just going to protonate that and you're going to have water plus. So do you understand that you either have basic conditions or acidic conditions? And if you try to put a base with an acid, all you're going to have is a weak nucleophile. And you won't even have acidic conditions because then it'll be neutral. For 9b, see, we have our unsymmetrical epoxide and we put under acid. Now, if we break, so now we're going to open this epoxide and we're looking at which bond to break. So if we break, we'll call this bond A, and this doesn't actually happen, this is hypothetical, because whenever you have a three-membered ring, folks, you don't have a carbocation. Okay, what if you break bond B? What does that cation look like? So this is a primary, and this would be a tertiary. So the tertiary carbocation would be more stable. So bond A would be actually more stable, and so when you do 10, this is going to do an SN2. So this epoxide here, this is very important, I would star 10, because you're going to have to be able to do this on your exam. So if you add acid and methanol, the first step is going to be protonation of your epoxide and acid. Now, your nucleophile, which is a weak nucleophile, can come in. And it's going to, since you have a three-membered oxonium ion, it's going to be sterically driven to this more substituted. So I put a delta positive. So even though it's not a full carbocation, you can write your delta positive. And then you're going to have inversion of stereochemistry. And then this is just going to get protonated in water workup. But you see how your OH and your nucleophile have anti-stereochemistry. And that's because, and it asks, that would be inversion. So after your group agrees on the product of the above reaction, consider the epoxide if you reacted with HBr. So what if instead of this nucleophile we reacted it with HBr? What would that product be? So you would end up having the Br as your nucleophile and your ring opening. (11) Consider the base catalyzed opening of the unsymmetrical epoxide. Under basic conditions, the neutral epoxide reacts with a nucleophile. Explain what kind of nucleophiles are necessary under basic conditions. Did you put strong? Because they're not activated. So under basic conditions, you basically have a negative charged nucleophile, and that means you have strong nucleophiles. So here we have an alkoxide, and the alkoxide now is going to come in and attack from the least substituted. Do you see that this has one CH3? This has two CH3s. So that is going to attack the least substituted, and then you're going to get your opening epoxide here. And here's your nucleophile. Okay, so we showed the electron form movement, and we see that it's attacking the least substituted carbon, and that's going to be because in an SN2 mechanism, it's concerted, and you get backside attack, and so backside attack is going to happen the fastest if it's the least hindered. And we're talking sterics here, so if it's least sterically hindered. At the carbon where the attack of the nucleophile occurs, what stereochemical outcome would come? This is inversion of stereochemistry. You have problems 12. Make sure you draw all your electron flow arrows, all your structures, and your products. Make sure you show your stereochemistry. 13, if you would like to do it for feedback, I will give that to you. We can make that a +1. So I'm not that worried if you do it, but if you want your +1, then you have to draw all your structures out, and you need the nucleophile adding twice, and you need to draw in your lone pairs for that nucleophile.